Where did I come from originally? Any guesses?
Manchester.
What? That is very specific. No.
Oh.
You're in the right country. Yes. England originally. No.
Somewhere.
Yes. Not Australia. I think having lived in Texas for 22 years, the combination of the sort of Texas drawl and a London accent combines to sound Australian. But I'm not Australian. I'm from England. Lived mostly in Scotland, though, which I'll talk about later on, because it's got a weird climate, Scotland does. And that's primarily what we're going to talk about today. We are going to talk about... Am I friendly too? Yeah, it's a bigger place than you think. It looks small, but it's bigger. We're going to talk about the abiotic factors that influence life on this planet and the distribution of life on this planet. So first of all, you tell me, why do we have seasons?
The way that the sunlight hits the earth.
The way that the sunlight hits the earth. Yes, it is to do with that. Let's dig down even deeper. What about the way the sunlight strikes the earth gives us these seasonal changes?
How much sunlight hits the earth at certain angles?
Yes, it's to do with an angle. Yes, anyone want to say contribute to this? The angle of incidence. Ooh, yes. That's technical terms now. So here we are. Here's a little diagram, very misleading, but helpful in some ways, that shows us what's really going on here. When I moved to Houston, I was told by some locals that I could expect to have 4 seasons, just like in Scotland, we have 4 seasons. But in Houston, the seasons were early summer, summer, late summer, and not summer.
Yep.
Which is kind of true here, I guess, as well, right?
Yes, sir.
Although you're about to get a cold blast. You see, next Tuesday, you're going to get some serious cold weather coming through here. It's going to freeze. It's going to freeze. Crazy. I love it when this happens. So, why though? I mean, right now, in Australia, they're gearing up in their swimming gear and getting the bikinis on and heading out to barbecuing on the beach.
Southern hemisphere.
Right. So this is what's going on with them right now. Okay, this is them today, essentially. They're in the southern hemisphere, and because of our tilt, right now they are temporarily angled more towards the sun in the southern hemisphere than we are. It's not much of a difference. It's very exaggerated in this picture, but it's enough to make a difference to how heat is distributed around our planet and seasonal change. But then 6 months from now, where will the Earth be in this diagram?
Like this, and that's
The
how it
northern
will
hemisphere will be
look.
facing the
The northern hemisphere will be getting more sunlight.
Yes, so the tilt stays the same. We go around the sun, here we go, and now we're over here. The tilt hasn't changed, right? The angle is exactly the same, but now this area above the dotted line, the northern hemisphere, is more angled towards, and so now we get to wear the swimsuits and bikinis and barbecue, and they're in their winter clothing. I've got friends who live in Australia, and they send me their Christmas photos, and it's bizarre. They're all on the beach having Christmas dinner in their swim gear, and it's baking hot, and they're all burning. What does Santa wear in Australia?
A tank top and flip-flops.
I don't know, it's weird, right? I mean, I can't even get my brain around how that works. All right, so you are right. Here's what's going on, but let's dig deeper. This is really a good explanation of what's happening. And you've got this diagram on the top right of your handout. So when you were a kid, you used to draw pictures in elementary school. Your teacher said, draw a picture of anything you like. And so you probably drew a house. And then you put some birds flying around, little bees, right? And then you put some clouds. And then up in the top corner, you had the sun with all the sunbeams coming out, yes? So here are the sunbeams. Here's our solar energy coming in. These are exactly the same, right? The amount of energy that's in this ray or beam, whatever you want to call it, is exactly the same as the amount of energy here. So coming to our surface is the same amount of energy. But look at what happens. What can you see on this diagram that's different in region A versus region B? Yeah, what about the distribution is different?
In rate A, it's much more focused and intense on one point, while in B, it's much more thoroughly distributed across.
Yeah, think about the surface area, where the X amount of energy is spread out over Y amount of area. Y, it'll be small here. Here at Y, the amount of area is enormous, right? So if we were to measure the amount of energy at any particular point, where would it be higher, A or B?
We
Yeah,
did it
for
with
sure.
like a flashlight. We put it like this, and there was more light right there.
Yeah.
We put it like at an angle. So there was more
Did you do that, lad?
Yeah.
You cut the things out and weighed them? Good lad, huh?
We did it on graph paper, so they were able to actually.
Oh, you calculated.
So we did
Well
same
done.
distance but different angle. And they were
Yeah,
able to
yeah, yeah.
calculate
Cool,
the surface
cool,
area.
cool, cool. So it's like, have you ever killed fire ants with a magnifying glass?
Yes.
Yeah, there's nothing more satisfying, guys. It's a great way to destroy an invasive species. So what you're doing is, the essentially you have this piece of glass that's circular like this. You have this much sunlight, but then the lens focuses down that much sunlight to this tiny little pinprick, and it's enough to set fire to an ant or paper. Awesome, you can burn all kinds of things. It's cool. That's what's going on here. So here it's like the pinpoint fire ant burning exercise. Same amount of sunlight up here, but it's a bigger area. It's like the lens hasn't focused it. It's all spread out. So that's what means here it's always going to be hot. Because sunlight, when it strikes the surface, tends to transform from sunlight into what? Heat. But it depends on the surface. Some surfaces, that doesn't happen a lot. Some surfaces have what is called a high albedo. Have you heard this word before, or is it not something you've addressed yet? Okay, good. So it's a new term. You'll talk about it more when you do climate, probably second semester, and climate change, things like that. Albedo is a measure of reflectance. And you already know about this intuitively. You have a deep understanding of this. It's summertime. You're going to go swimming with your friends. You're walking barefoot to their house. You walk on the blacktop or on the grass?
Grass.
Yeah, why?
The black,
You burn your feet off, right?
Bro, it's so hot that it feels cold.
Yeah, that's
I'm
what
sure I'm
happens to
following
me. I
on that.
walk on the blacktop.
No, you know what I mean? Like,
Really?
walking
Yeah.
barefoot,
Oh,
so
no, it's
hot,
not.
it feels
All right,
cold.
put it this way. You're going to the mall, you're going to go somewhere with some buddies, you're getting into two cars. It's the middle of July. One of them is a silver or white car, one of them is black. You get in the silver car, right? It's going to be not as hot inside that car. It's to do with these weird thermodynamics that happen when you have different colored surfaces and different textures as well. The most reflective surface on Earth is what? Naturally occurring surface. Yes, fresh snow. So think about, where do you find a lot of snow? Right, high altitude, but also latitude, North Pole, South Pole, where you've already got less energy anyway. The reason there's a bunch of snow is because it's cold, right? But then what sunlight does come in, bounces straight back off again, right? It doesn't convert into heat, it reflects. This is why if you go skiing, when I grew up in Scotland, we'd go skiing from time to time, and you'd have this crystal clear, cloudless day, it's freezing cold, and everyone gets sunburn under their chin, right here. Weird, and under their nose. You get big old blisters under your nose, and under your chin, and under your ears, right here. It's bizarre. It's because it's just reflecting off, and here is where it's burning you. It's crazy. So snow is highly reflective. Blacktop, look at that. Not reflective. 5%, 10% albedo. That's why it's so darn hot. In fact, there's some roads we've got in Houston, you probably have them here, where it melts. It's so hot, it's sticky. It's crazy. All right, so humans can alter this too. We can change the surface. So as we're thinking about where life is distributed, the main thing is to do with sunlight coming in, at least on land, right? But the surface matters as well, because if it's highly reflective, it won't feel very hot there, even if you've got a lot of sunlight. So check this out. Which of the following contributes to the unequal heating of the Earth? This is a good example of what we call a multiple choice. There are not a lot of these on the AP exam. There's maybe 6 through 9, maybe. Out of the 100 that you take, there's only a few of these look like this, and they're kind of a nightmare, to be honest. I've always hated these. Why? Why do you hate these kind? I know, the longer you think about it, the more confused you get, and the more you start justifying, well, that one could be, I can think of a scenario with that one. You know, you really have to start cutting down on it. It's hard. And before you know it, 5 minutes have gone by, and that is a killer for your grade. When we get the score reports for the release tests, the last 5 to 10 questions are always lower on average than everything that came before. Why? Finish, right? You've got 100 questions, and how much time have you got to do those 100 questions? 90 minutes. So per question, less than a minute. If you spend 5 minutes on a question, you're screwed. So don't. Oops, sorry. I'm on video. Your grade will be negatively impacted. All right. So
The other thing I always tell them too is that if you have to talk yourself into a question, it might be, you could think of one scenario that would be an exception to it, but on the AP exam, like, you could talk yourself into exceptions all over environmental science. It's the most correct. So if you have to talk yourself into it, it's not correct.
that's the problem with this exam as well, is that it's not like some of the teacher type tests that you get, or textbook test bank questions where there's a clear right answer. So many of these are, which is the best explanation? Which of these is most likely to happen? They might all be likely. You go, which one's the most likely? I don't know. So with this, same strategy though as you would take with a regular multiple choice. What you want to do is, first of all, go in reverse though and start with, which of these statements do I know is definitely one of the ones I need? So let's pick one of these three that we think. Yeah, number one? I agree. That's where I start. I think I know it's got to be one for sure. The angle is that where it hits at, the angle of incidence, that definitely contributes to unequal heat. So it's definitely number one. So even before we go any further, we can eliminate some answer choices.
C and D.
Yeah, C and D are gone, right? Don't even think about those anymore. It's not C or D. So now you decide, well, could it be any of the others? Is there anything else that you feel pretty confident? I think it's got to be that too, sure. Two, right, the angle. We already saw that. The surface area, the angle and the surface area. Those two things. So now we can eliminate another choice. A is gone. We've got it down to two choices, and it only took us about 30 seconds to do that. So this is a question where you stick with it. If you can't get it down to two answer choices within 30 seconds, move on. Circle it in the booklet and just come back to it later. Don't be that person that doesn't get the easy ones at the end of the test because you spent 5 minutes racking your brains on this one. Skip it. But we got it down to two, so let's go ahead and finish this question. What are we going to go with? Is it 1 and 2 only, or is it 1, 2, and 3?
1, 2 only.
It's tough, because clouds do reflect sunlight. That's a true statement, actually, right? But it's not asking us which of these is a true statement. It's asking us which of these contributes to unequal heating of the Earth. Clouds do not contribute to the unequal heating of the Earth, because they come and they go, and they move, right? And so they even out, essentially. They do not have any significant influence on the reason why it's colder here, warmer here. Clouds have a negligible impact, and that's why I would eliminate 3. So your answer would have been B. So, I think it's the only one of these we're going to do today. I can't remember. But most of the rest of them are. So we've talked about sunlight coming in, striking our planet. Where is sunlight always striking our planet with high intensity? The equator. All right. So it's always warm there. That makes sense. It converts into heat. It's hot. That heat is going to heat the air. What will the air start to do? Rise. Always. So there's no seasons on the equator, right? So it's always rising. Every day, your air is leaving. So do you suffocate if you live on the equator? Why not?
Because
It's
air
weird.
is falling all day long.
You've got some other air being pulled in. That's what wind is, right? You've got rising air that's drawing in air from other places where it's sinking. That's what all it is with wind. So the air is always rising on the equator, and there's so much ocean. If you visualize a world map, you've got so much ocean around the equator. So this air is not only hot, it's moist. You know, that's one of the world's least favorite words in the English language. Moist. I think it's an excellent word. You've got moist, hot air. All right, it's hot, it's humid, it's moist, it's rising. Now, as it goes up in altitude, what is that air going to start to do? Cool down. It's carrying all this water vapor. So it's going to condense in clouds and dump a bunch of moisture. So what kind of biome would you expect to find all along the equator? Tropical rainforest, right. And as long as these continents are in that position, there's been rainforest all the way around there. If the continents move, and they will, 100 million years from now, maybe there'll be rainforest in Alaska. Could be. It all depends. If Alaska comes down to the equator, then it'll be a rainforest. It's to do with the heating of the Earth from this angle of the sun, and then these convection cells that never change. Doesn't matter what's going on with the continents underneath. These convection cells have been in existence for billions of years on our planet. Ever since we've had an atmosphere, they have been rolling around, rising and falling and rising and falling. So here we've got rainforest. It's hot, it's moist, it's dumped all of its moisture. The air gets pulled towards the poles, but it's cold air. So what's it going to do? Sink. And look at where it sinks. 30 degrees north and 30 degrees south. The Tropic of Cancer, the Tropic of Capricorn. It's cool, sinking, dry air. So what kind of biome would you expect to find here?
Desert.
And here. Yeah. And that is exactly what we do find around the planet. And it leads to this thing that's mentioned in one of those little FRQ things, 1 or 2, I think. The ITCZ. You ever heard of this? I bet, yeah, probably not. This is the Intertropical Convergence Zone. Why do you think we call it the Intertropical Convergence Zone? It's like a convergent boundary in plate tectonics. What's converging here at the equator?
The cells.
Yeah, the wind is, right? There's all this air on the surface which is converging on the equator. All the way around our planet, the air is converging. Winds blow towards the equator between the Tropic of Cancer and the Tropic of Capricorn. 24/7. And they blow in a straight line. See, it's just straight down the tropic and straight up again, and round and round it goes. So you've got to visualize these cells kind of like donuts, like a ring of air that's constantly rolling around, and has been doing that for billions of years. But wait a minute, something's weird about this. The air is flowing in a straight line. So what the heck is going on here? What's with these? Why is it curving?
Coriolis.
Ooh, Coriolis effect. That's a big word. Can you explain what that is?
It's like the rotation of the Earth.
Uh-huh. Yeah, so the Earth is rotating. Which way are we rotating? It depends on the clock, right? Like, I noticed this one this morning. That one really
I
messed me
bought
up.
that one in Australia.
It's so, that's cool. Yeah, I was like, what is, oh, I see. Yeah, no, we spin counterclockwise. So we're going round this way. So the Earth is moving in that direction. It's spinning that away. So what's going on with these winds? Well, that's a terrible thing. Right, they are. They stay still just like that, but the Earth is spinning underneath it. So you get this weird effect that starts to happen. But note, I like this diagram. Look, it shows you, here's our rainforests, and then on the outside of these two cells, you get two bands of desert all the way around the Earth. And then you've got more moist air here with forests and another cell, and then a polar cell at the top, keeping those ice caps nice and cold. The thing about the intertropical convergence zone is, remember the tilt? Right, we're not straight up, straight down. This doesn't stay static like this, because we're tilted. The equator is tilted too. So, for our winter, let's say, where it's January, February, whatever, where's most of the sunlight striking the Earth, northern or southern hemisphere? Southern, all right. So what happens is this convergence zone shifts a little bit towards the south for 6 months. And then when it comes to be our summer, June, July, August, those kinds of things, well, now it's shifted up this way a little bit. So the equator is still getting tons of rain all the time. But the boundary, where does that rain end? It shifts southwards in the winter months for us, and northwards in the summer months, and it kind of flip-flops backwards and forwards, and that creates these weird climate zones around the edge of the equator. It's a good way of looking at it. Here's the straight lines blowing here, and then here's it curving. Got a great little video I can show you, actually, if it works. It should do. You might have seen this one. Have you anyone ever gone on a roundabout? You know, little merry-go-round roundabouts things as a kid? Spin. Where's the funnest place to be on those? Yes, the edge, right. You stand in the middle, it's not much fun. You just kind of do this. It's very exciting, right? But if you're on the edge, you're like, ah! You know, like this. In fact, there's some really cool YouTube videos of somebody who, they got like a dirt bike and kind of laid it on its side and put the rear wheel where the power is and lined it up with the edge, got a bunch of kids on there, and then slowly revved up the engine. So it's going about 40 miles an hour, and they're flinging children in every direction. It's hilarious. You should check it out. It's awesome.
They obviously had pads, right?
No. Actually, they were teenagers. I think they signed up for it. They agreed to kill the lights, yeah.
With a simple game of catch, I think I've found a way to show an effect that will have you doubting your very own eyes. Now, they don't know it yet, but our budding ball players sitting on our specially rigged merry-go-round are about to demonstrate a rather astonishing optical illusion. Right, here's the game, right? You're going to throw the ball straight to, what's your name, Victor, right? But this time, I'm going to complicate things slightly. I'm going to rotate the merry-go-round counterclockwise. So you throw it whilst it's moving. What's going to happen?
I don't know why, but I feel like if we're going fast enough, like I might actually be the one catching the ball.
Okay, so you're going to throw it and you're going to catch it, all right?
Yeah, I don't know.
What's going to happen? I was going to veer off to the left. So the ball is going to swerve off to the left, and you might catch it. Awesome. Okay, good. Right, so what's going to happen?
I think it's just going to come straight to me, and I'm going to catch it like the champion that I am.
Show me the catch. Okay, good. Right, okay, is that everyone? No, hang on, one more. Spencer.
It's not arrogant.
Just quietly confident.
He's not catching it. No.
So what's going to happen to the ball?
I'm catching it. It's right here.
Great, so we've got one saying to go off to you, one saying comes to you, Spencer, and you think it goes straight ahead, but you think you'll be the one catching it.
Yeah.
Now remember, the ball will be thrown straight across the spinning merry-go-round, but where will it end up?
What do you
Will it be
think?
caught by
Make your
the thrower?
choices here.
Will it be caught by the person opposite? Will it be caught by the person to the thrower's left? Or by the person to the thrower's right?
What do you think?
Right, in your own time, throw the ball. So the answer was D. It was caught by the person on the thrower's right. Our camera angles seem to show the ball bend in the air. So is that a camera effect, or are we seeing what they saw? Hang on, this couldn't get much more simple. The idea was just to throw the ball straight to Victor to show us his amazing catching skills.
That's right.
Yeah, it did. It just curved right over this way.
So let me get this straight. So somehow you threw the ball, it left your hands, and then what?
And then it just got sucked over to him.
In the air.
Yeah, I threw a perfect throw.
What did you see?
Yeah, curved right in.
Right, so we all agree here the ball curved in midair.
Yeah.
And you didn't cheat this at all?
No, I didn't.
Okay. And do you know why it did that?
No.
No idea. It's called the Coriolis effect. And it's very simple. It's objects in motion appearing to be, it's an optical illusion, appearing to be deflected off their intended course. So what's actually happening here is you are throwing this ball. You can only throw a ball in a straight line. Can I clear that up straight away?
Yes.
Even though it appears in your eyes to be bending. So you throw the ball straight, it's still going straight, but the table is moving below you, and all of a sudden, look who's in front of that straight moving ball, and it looks like it's bent off to the right because you're still looking at the guy you were intending to throw to, and that, ladies and gentlemen, is the Coriolis effect.
All right, so it's a really odd thing. It's kind of an optical illusion. It's like, the way I think of it is if you've got, like you bought a vinyl record, you got an LP, you put it on the, you're spinning it on the turntable, and you want to draw a straight line. You'll get a ruler and a Sharpie, I'm going to get it's going to be a straight line. I'm going to get it start in the middle, let it spin, 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 I'm going to go as fast as I can, boom, straight line. I drew a straight line. But when I lift it up and look at it, it's not going to be a straight line, right? Because the surface I was drawing on moved underneath it. That's kind of what's happening with the Coriolis effect. There's another video which I don't really have time to show you, but it explains it a little. It sounds like you've already had some explanations on this, but it's like, so it's to do with the rotation, right? We're completing the same rotation. We're doing 360 degrees in the same amount of time. Here and here. But think about the circumference of the circle that's going to be turned here versus up here. You're going to cover way more distance in the same amount of time. So if you're covering more distance in the same amount of time, it means the velocity is much, much higher. So this is spinning much, much faster than out here. That's why it's more fun on the edge of the merry-go-round than in the middle. You're going faster. So, but you throw this, and when you throw the ball, it doesn't change velocity at all. It's still traveling at whatever speed you are traveling. So if you throw it from the North Pole, where you're hardly turning at all, your velocity is whatever it is, and it's not high, it's low. So you throw it. People here, though, are traveling much, much faster than this, so they've already moved on. So the ball looks like it curves because the person who catches it is standing here. It didn't curve. It did go in a straight line, but from the perspective of looking down on it, it looks like it threw a curved line. Make sense? All right. So we've got winds that blow towards the equator in the intertropical convergence zone. The other thing that distributes heat is the ocean. Ocean currents do a big job in distributing heat. If there weren't any ocean currents, the water at the equator would always be boiling. Just get hotter and hotter, just roll around. But because of these weirdly shaped continents, you've got rising water, sinking water, and it pulls this water all around our planet in this weird pattern. And so this particular set of arrows changes depending on where the continents are. So if this was Gondwana land or Pangaea or Rodinia, one of those supercontinents, it would look totally different. Those cells in the atmosphere wouldn't. They're identical and have been for billions of years, but because of plate tectonics, the ocean currents shift and they change with time. I'm from here, right here in the north of the British Isles of Scotland, right there. We are always about 20 degrees warmer than Anchorage, Alaska. Even though we're basically the same latitude, we're always, whether it's winter or summer, 20 degrees warmer, at least. Sometimes 30 degrees warmer. Why?
The ocean currents.
Yeah, the angle of incidence is the same. You get exactly the same amount of sunlight, and that converts to the same amount of heat. We have extra heat where we are because of this current. Anyone know what it's called? Comes out of the Gulf of Mexico. Close. The Gulf Stream is what we call it. It brings hot water across the Atlantic, and the winds blow across Europe that way, delivering all this warm, moist air. So we're always way, way warmer in northern Europe than we are in Canada and Alaska. Way warmer. So ocean currents are important. Atmospheric cells are important. You might have been paying attention earlier on to the diagram that named these, but even if you weren't, you can eliminate here. The question's asking, and it's a traditional multiple choice, which of the following is the correct order of convection cells starting from the equator? So if you're starting at the equator, you can already eliminate 2 and 3 here. What would you eliminate? A and C are gone for sure. You wouldn't start with polar if you're at the equator. And E as well, because it wouldn't be in the middle, it would be at the end. Right, it's got to be the last one. So it's B and D. Anyone know?
Feral,
Wait, can
hadley,
you explain
polar.
what feral and
I did though.
Maybe.
We covered that.
Here.
Yeah.
Yeah,
These are the two Hadley cells above and below, then the two feral cells here and here, and then the polar cells here and here. They're like rolling donuts of air. You can see it kind of cut away there. Imagine this going all the way around the planet like a rolling ring. Here they are again. That's a good way of looking at it. There's the Hadley cell, here's the polar cell, here's the feral cell. We've cut it away so we can see the surface, but it's like a permanent donut, a ring of air. So the answer is
D.
yes, D. Well done. Okay, so all together, those things, the ocean, the sunlight, the convection cells in the atmosphere together create this distribution of life on our planet, which we call biomes. And really quickly, we're just going to fly through those biomes because the only thing you really have to understand about biomes, you need to have memorized a couple of characteristics. You probably did that in elementary and middle school, right? What's different on the AP exam is you've got to be able to read a climatogram or a climograph and interpret it. So let's get a look. First of all, let's see if we can name them. What is biome number 1? Tundra, good. What is biome number 2? It's the biggest by far of all the terrestrial biomes. The taiga, excellent. Or sometimes called boreal forest. What's number 3? Temperate forest. Yeah, temperate forest, temperate deciduous forest primarily. Number 4. We got a lot of this in the Midwest of the United States. Yeah, grasslands, the plains, the prairies. Number 5. Along the equator. Tropical rainforest. Number 6. Right here, and then a little bit on the tip of South Africa, some down here in Patagonia. Actually, not quite Patagonia, further north of there. Little bit on the southern California. Not a desert. It's similar. It's weird. It's very distinct in terms of its vegetation, which is how we name the biomes, by their vegetation type. But very, very distinct. It's found around the Mediterranean, but it has another name. It sounds kind of Spanish.
It's my favorite
Chaparral. Yes, it's an amazing biome. So let's get a look. First of all, if we look at the tundra, what are we going to expect to see when we think about climate? So temperature, precipitation, cold and dry. Yes, it is. Now, this particular climatogram is from Reykjavik, Iceland. It's very unusual. Iceland is in the tundra zone in theory by latitude. This is a lot wetter than a typical tundra would be. Tundra is a type of desert. But look where Iceland is. Right there.
It's an island.
It is. So why does it get so much more rainfall, do you think? Remember that? What did we... same reason Scotland does. Yeah, the Gulf Stream goes right past it here. So it's got a lot of extra moisture than most... than most of them you'd expect. So you get... Typically a tundra is very dry. It's a type of desert. And if there's a type of desert, what do you never see growing in deserts?
Vegetation.
Well, you don't get a lot of vegetation, but you certainly don't get trees. Trees are very thirsty. They need constant rainfall. They can go without rainfall for a month or maybe 2 if they've had a lot throughout the rest of the year, but if it goes more than that, they just can't grow. And they're tall, so they need roots. So why can't they grow here? Permafrost. Yes. So maybe 100 years from now there will be trees in the tundra. When you're losing the permafrost, maybe they will start to grow. Taiga, what are we going to see here? When we look at this climatogram. Well, how's this going to be different from the tundra, do you think?
More moisture.
There's more trees, which means more moisture. Good. What about temperature? Warmer or colder?
Warmer.
A little bit warmer, right. But still not what you'd call like tropical, right? Check it out. Let's get a look at these. Sometimes these can be hard to read, because what they like to do is ask you a question like, what is the average precipitation in July? And the answer choices will be 10 centimeters, minus 40. Or they might say 35 centimeters. Could be your answer choices. What's the answer?
Minus
10. So you've got problems with these graphs, right? Because they've got 2 y-axes. And then when they're in color, there's kind of a clue as to which one is which, right? You've got blue and red. They match. Your test isn't color, though. It's black and white. So you've got to memorize this. Precipitation is always on the left in centimeters. Temperature is always on the right. But how do you know which graph to read? Well, the easiest way I can think of to memorize this, and what I tell my students is, visualize this precipitation data like a rain gauge. It's like a measuring cylinder, filling up with water. So that's the histogram or the bar chart is precipitation because it looks like a rain gauge. It's a rain gauge. It's measuring the amount of precipitation as it comes up. This is your temperature. So now, what is the average precipitation in July? 10 centimeters. Don't fall into the trap that they'll set for you where you're reading -40 or you're reading up here. You got the axis right, but you got the line wrong, 35. You got to make sure you're reading down here and you're reading off to the left. Okay? All right. That's taiga. Which statement then about tundras and boreal forests is correct? It's a traditional multiple choice. You've got less than a minute to answer. We're going to start eliminating and see if we can get it down to 2 choices. So what would you eliminate? B. Tundras are warmer than boreal forests. Yeah, that's definitely not true. They are cold. But we get rid of B. Anything else?
C.
It's definitely not true. Yeah, C. Boreal forests have a shorter growing season. No, they don't. Notice we got a much longer growing season. Anything above 0 degrees Celsius, plants can do photosynthesis throughout the day. And look, they've got a long growing season, plenty of rainfall. That allows trees to grow because they've got a longer growing season. So we got rid of B and got rid of C. Anything else you'd get rid of? D, yeah, plant growth in both biomes is limited by precipitation. No, it is in the tundra, but not in the taiga. There's plenty of rainfall in the taiga. So B, C, and D are gone. We've got it down to 2 choices, A or E. Which of those is true?
E.
It is E, yes. Actually, the thing about these colder environments is organic matter builds up and accumulates a lot. You get thick, thick mats of vegetation that's dead but hasn't decomposed. It's too cold. And that's one of the other reasons we're worried about climate change, is the tundra is melting and all of that. You know, you could have 20, 30 feet of plant material sitting there waiting to decompose if it thawed out. And when it does, you start to produce methane, carbon dioxide, and all kinds of stuff. So temperate forests, what are we going to see here when we look at the climatogram?
A lot more trees.
Well, yeah. Different kind of tree, though.
Yeah.
What kinds of trees
A
are
lot more
these?
precipitation.
What do we call these kinds of trees? They're not the same as these kinds of trees. Deciduous. Yeah, what does that mean, deciduous?
They don't have needles, they have leaves.
They have leaves, and what happens to those leaves? They fall in a season. Huh. Why do they fall in that season? What do trees need a lot of? It's not so much the temperature. It's usually to do with precipitation. And growing season, that's true. Where they are, whether they're far north or not. Check it out. We've got plenty of rainfall here, long growing season, but it does go below freezing for a short period of time. These leaves are much more vulnerable to freezing. They can die, right? If they were photosynthesizing when the water was solid instead of liquid, it would burst those cells. They are not well defended against cold temperature, so they drop their leaves because they don't have to do it for very long. The growing season is so long, they've only got to wait a couple of months where they drop the leaves. They can store what they've got. They don't die. They're just waiting. What about grasslands? What will we see when we look at the grasslands? Well, yes. So what about the climatogram? Think about it. There's no trees.
Not much precipitation.
Yes. So check this out. There's 2 kinds of grassland. Tropical, which we call savanna. Look at that temperature. No change. It's on the equator, or close to the equator. Lots and lots of potential for growth, but what limits it is water. You've got a couple of months there where it's really dry. Trees can't survive. And then look at this temperate one. Again, we've got a nice long growing season, but look, it does get down to freezing point. But look at the rainfall. The reason it's not a forest here is because we've got very, very low rainfall in January, February, and December as well. Not enough to support trees. So that's why the grasslands dominate. Trees are thirsty. When we look at the tropical rainforest, what will we see?
A lot of large trees. A lot of precipitation. Warmer.
Wow. There's a reason it's called the rainforest, guys. Most of my research before I got into teaching was in tropical ecology. So I worked in South America, in Guyana, studying giant otters in the rainforest, and then after that in Madagascar, studying fruit bats, giant fruit bats. 6-foot wingspan fruit bats. That's a big bat. And we got smarter the second time we did one of these long-term expeditions, and we wore more synthetic clothing. The first expedition we did in Guyana, we were only actually in the forest living there for about 3 months. But in that time, all of our cotton clothing just rotted off our bodies. So we ended up, at the end of that trip, none of us had any underwear at all. Everybody was going commando, guys and girls. The only clothing that survived was the synthetic fiber clothing. So I had some pants, fortunately. Some people didn't. It was bad. We looked like a bit of a state when we came back in from the field. But that's one of the reasons why most of the folks who live there, the indigenous populations, they're not wearing shorts and shirts. They're just wearing nothing most of the time. Because what's the point of making clothing that just rots so quickly? decomposition is constant. There's one other kind, though, of forest that you get here. Tropical, notice, there's no seasons really in terms of temperature. It's hot all year round. So what is different about that tropical deciduous forest versus the rainforest?
The rainfall.
Yes, highly seasonal. Huge rainfall most of the year. So that's enough to keep the trees alive during those 2 months, but they're deciduous trees that grow here. Here, they're evergreen, which means they drop just year round, randomly. It's not like a season where they all fall off. These, though, it's seasonal leaf senescence. And look at what's happened here. Just 2 months of dry, there's not enough active available water to do photosynthesis, so they dump their leaves and then it all grows back again. Last of all, we've got 2 more. Mediterranean, what are we going to see here? There's shrubs, there's no trees, so what will that tell us about the rainfall? Yeah. There's also no grass. So yeah, this is very dry, check it out. How the heck do these shrubs grow? Well, because there is rainfall, and there's quite a lot of it certain times of year, which allows biomass to grow and bloom and flower, but then it all dries out and dries up, and the only things that survive that are these shrubs that are heat and drought tolerant. They've got needles and spines and very tiny little leaves and succulent plants like they get in the desert. Very common in California, but they're experiencing a lot of what right now? Drought and fires. You see the news, these massive forest, these wildfires that are blowing through. Because you've got this biomass builds up during the winter time and there's plenty of rain, but then it just dries out like kindling. It's literally like paper, this stuff, and it catches fire so easily. Last of all, desert. What will we see when we look at this climatogram?
Very, very dry.
Yes. I'm glad you said that. It's got nothing to do with temperature. A desert is a desert because of its rainfall. You can get cold deserts, hot deserts, frozen deserts, tropical deserts, and everything in between. The key issue is rainfall. The only reason there's any vegetation is because the vegetation that can make it is cactus. They're highly adapted to a little tiny bit of rain. When it happens, they catch it all and store it, sometimes for over a year before they can get any more. So you never get trees, you never get grass, you never get shrubs, you just get this kind of plant life. Okay, so let's answer these questions. Why do we use plant life to categorize the biomes? It's a multiple choice, so we should get to eliminate. What are you going to eliminate? B. Different plant growths indicate climate differences, whereas animals don't. Yeah, that's not true. Animals indicate it too. There's a reason there's no snakes in the tundra and there's no polar bears in the rainforest. That animals can indicate what's going on with the climate just as well as plants. So that's not the reason, so it's not B. Anything else? C. Plants from similar climates evolve different adaptations? No, that's not how evolution works. They're the same adaptation. What else? E. Similar plant growth forms exist in both terrestrial and aquatic biomes. There's forests in the middle of the ocean. No, there's not. There's no trees out there. They're not the same plant growth forms. So we got rid of 3 in 30 seconds. Let's keep going. So our choices are, we got to go with, what was it, A or C? A or D. All right, yeah, we got rid of C. A or D. What do you think? It's D, yeah. The reason you have similar plant growth forms and why they are a useful way of calling it a rainforest is because even though there might be totally different species, they look the same because they live in areas that have the same temperature and precipitation. Guyana in South America has a tropical rainforest ecosystem with completely different trees and species to the ones in Madagascar, but they look exactly the same because the climate is exactly the same. Now what about this? Which statement best explains why polar regions are cooler? It's not asking which of the following is a true statement. It's saying which of these explains why the poles are colder than the tropics. So again, let's eliminate, get it down to 2 choices in 30 seconds if we can. What would you eliminate? C. Tropical regions receive less direct sunlight. Yeah, that's not true. We eliminate C. What else? E. Tropical regions rotate at a faster speed than polar regions. That might be a true statement, but it's not the reason why it's colder. D. Sunlight travels through more atmosphere and loses more energy in the tropics. Yeah, that's not true. It has more energy in the tropics. So what did we get rid of here? We got rid of B and no C, D, and E. We got rid of B. So C, D, and E. Is that right? Yes. So we're down to A and B. Remember, what are the most reflective surfaces on Earth?
Snow.
Ice and snow. High albedo with ice and snow. So yes, the answer is B. Well done. So you see how even if you might not be certain of some of these answers, you can eliminate things pretty quickly. And if you get it down to 2, guess away. All right, well, let's go to some aquatics real quick. Oh boy, we've got 20 minutes to talk about aquatics. This is going to be fast. Okay, so life in the water is very different from life on land. On land, really the two defining features that determine where things are found and why they live there is temperature and precipitation. That's it. But in the water, there's a lot more stuff that can vary other than just the temperature and the rainfall. First of all, you're in the water, so you're not worrying about precipitation, right? So what else is there? What else can influence life in the water? Yes?
Salinity.
Salinity, yes, that's a big one. What else?
Sunlight.
Yes, how far it penetrates and how much of it. Good. What else?
pH.
pH, yes, acidity, basic, neutral, that can vary. What else? Nutrients, sure. Nutrient levels in the water. If you won't get a coral reef if there's too many nutrients, you get something else. What else? Yeah, temperature varies by depth a lot. What else varies by depth? It can, yes. Water pressure, sunlight going through. Yeah, man, there's so many things. Also, think about why is life in a river different from life in a lake?
Moving along.
Yeah, one's moving, one's not. Salt water, fresh water. Wow, there's just so much to think about. So life in water depends on a lot of different things. And because of that, they like to ask questions about water a lot. So let's get a look. We categorize these biomes, for want of a better word, aquatic systems. We already broadly divide them into two fairly arbitrary categories. What are the two fairly arbitrary categories?
Fresh and salt.
Fresh and salt. Okay, so which one's saltier? Ocean or rivers?
Ocean.
Yeah, but wait a minute, how did the salt get into the rivers? I mean, how did the salt get into the ocean? Why is it so salty? How did the salt get there? From where?
Erosion. Knocks down.
Carried down by
Rivers.
rivers. So, rivers are salty. They have to be. That's how the salt gets into the ocean. It's carried in by rivers. So don't think that don't have this idea that fresh water means no salt and salt water means it's got salt. No, the salt that's in the ocean came from the rivers. So there is salt in the rivers. It's not a lot of it. So why does it go so high in the ocetion then? Why does it get
all
saltier?
the rivers are converging.
Okay, so they're delivering all this salt 24/7 in. That's one reason. So it kind of doesn't have anywhere to go. But why don't the oceans just constantly keep rising then until we overflow?
Rainfall.
Evaporation. Okay, so you're on a desert island. You just got shipwrecked. There's no fresh water. You're going to die. Unless, what would you do? Okay, yes, it rains. If it doesn't rain,
Filter water.
filter it. Good luck with that. It's hard getting salt out of water. Boil it, right? You boil it. And you collect the evaporate and condense it. And it's pure H2O, distilled water. Where's the salt? Behind. So now think about the ocean as a giant boiling pot of water. All that sunlight striking it. It's evaporating. The water leaves, but the salt does not. And it keeps having more salt delivered by rivers all the time. That is why the ocean is saltier. So let's get a look at the fresh water first of all, because honestly, that's what life depends on, is fresh water. If it's too salty, nothing can use it. We can't drink it. Well, you could, but what happens? You could die, or you puke, you gag it up, right? Several. Trees can't use it. Only one kind of tree can use salt water. It's a mangrove, and it has adapted to suck the salt into sacrificial leaves that it pumps the salt in, and they drop it off and put it back in the ocean where it came from. But look at this. Look how much fresh water there is on our planet. No. So, can we get more water? How do we get more water on our planet?
You can't.
No, you can't. It's fixed. Whatever's here has been here for billions of years. Well, I guess the last comet struck about 160 million years ago. That carried a bit of ice. And that was it. So since then, there's been no new water. All the water that you're currently drinking has always been here. It was in something else before it was in you. In fact, it was in millions of things before it was in you. Millions of people probably as well.
All right.
We're drinking people right now. We all are. Okay, but let's look at the fresh water. Where is it? It's only 2.5%, so it's pretty precious. But now think about this from the perspective of wildlife and nature. Let's zoom in on it. Where is most of that fresh water?
Glaciers.
Solid water. Nothing can use solid water. There's no cell, no living thing on Earth can use solid water. It's got to be liquid. So that's not useful to plants and animals. Groundwater. Misconception a lot of students have. Groundwater sounds like water on the ground. It's not. It's thousands of feet underground. Plants and animals can't use that either. We can drill for it and get it out of it, and have done. Like 1,000 times faster than it's being replenished, by the way. But look at that. So between these two, not useful to plants or animals, that's 99.7% of the fresh water is not useful. So all of the lakes and rivers and streams and ditches and ponds and bayous and swamps and wetlands, all of that is 0.3% of 2.5%, which is about 0.0012% of the water on Earth. That's it. That's all the water we see that's flowing and visible and sitting right there. Isn't that frightening? It's hardly anything. It's tiny, tiny amount. And what are we doing with this water?
Drinking.
Well, yeah.
Drinking, powering cities.
And polluting it and wasting it and doing all kinds of things, right? We should be a lot more careful about our water. But wait a minute, though. I think we should ban it. It's dangerous. Look, fact, water is the leading cause of drowning.
Oh, right?
Dangerous, man.
Bro, they
Dangerous.
won't drink the water for some
Oh, but
reason.
wait, hold on. Look, 100% of people exposed to water will die.
Dude.
And 100% of all serial killers and drug dealers have admitted to drinking it. I'm telling you, it's deadly. We should be, yeah, it's jokes, but everything's fatal. The thing about concentration is anything will kill you. I mean, you might have had a bag of Skittles this morning. Maybe you had 2. Maybe you had 3.
I haven't had any.
All right, did somebody stole them before you got to them?
No, I just.
What would happen if you ate 300 bags of Skittles?
You're gonna die.
Dead, right?
Diabetes.
Well, yeah, well, you die now, die later. You'll die pretty quickly if you ate that many in like one day. That's just a toxic amount of sugar. Salt's the same. I like putting salt in my fries, but I wouldn't dump the whole box of salt on it, right? Because I'd die. That everything will kill you. It's about concentration. And animals and plants have to worry about that when they're in the water because it varies. When we're on land, what's in the air doesn't vary very much, but in the oceans, in lakes, in rivers and streams, the concentrations of different chemicals can vary dramatically and can be toxic, especially in what we call lentic ecosystems. Lentic, you've got to define this somewhere, I think, means not moving. Which type of ecosystem do you think is more likely to be susceptible to pollution? Moving water or stationary water? Yes. Why?
Because there's nowhere to.
There's no outlet, right? It's going to just, whatever's there is there. If it doesn't break down and disappear, it's going to be there a while. And the fish can't just get up and walk. It's not like Dr. Seuss, guys. Sorry to break it to you. The humming fish cannot just wander away to a new habitat. They're stuck there. Whereas in a river, we can get away from that stuff. So they are very susceptible. We're going to look at them first, and we put them in 3 broad categories, these types of lakes or ponds. First of all, we have what we call oligotrophic lakes. Beautiful lakes. What do you notice about these lakes when you look at them?
Blue water.
Clear, crystal clear, sunlight all the way to the bottom. Why is it so clear?
Not minerals.
Minerals. It's not really to do with the minerals. What do you say? Yes, so not a lot of sediments being washed in here, and that's usually because of where they are. They're up high, they're not at the end of the floodplain where there's loads of sediments coming in. They're at the source waters of where a watershed would be, so they're not getting a lot of stuff coming in. That's true. The main reason why that is because of this. Oligotrophic lakes are low in nutrients. And it's not the nutrients that makes the water cloudy when the levels go up. Why does the water start to look different when you start raising the nutrient level? Why isn't it clear anymore if you keep adding nutrients? It's not, well, it's not things die. Things grow. What grows? What's going to feed on those nutrients? Algae. Algae. Yes. So here in an oligotrophic lake, low nutrients means low algae. And also, what do you think? High biodiversity or low biodiversity? Low, very low. So jot that down too. Oligotrophic lakes, they look beautiful. Great photographs. There's not a lot going on in an oligotrophic lake because there's very little nutrients, which means very little algae. And if you've got very few producers, then you're going to have very little anything else. Then there's this kind of lake, the mesotrophic lake. Meso means middle. So it's got medium nutrients. What do you notice is different in this lake? Look at that diagram. Oh, let's see. How is that lake different from this lake? A lot more biodiversity. High. In fact, the highest biodiversity of all these kinds of lakes is right here in the mesotrophic lakes. Why is it so high? Let's get a look. What do you think? It's got more nutrients, so algae can grow.
It has an average amount of nutrients they can blow up.
Sure, so you've got, it allows some algae to grow, but not too many. As we'll see in a minute, things get weird when there's too much nutrients. Because there's medium nutrients, sunlight can travel all the way to the bottom. It's not these thick mats of algae and green slime. It's fairly clear water. Sunlight can travel down to the bottom, and because of that, plants can root down here, grow their stems and leaves up through, and even expose out the top. So there's all kinds of life available in a mesotrophic lake. Now look at this next one, the eutrophic lake. What's going on here? How is that different? It is. It's very green or brown. It's got really high nutrients. You'd think with really high nutrients, that would mean more what? Right. More, right, you'd think. Because there's more algae, right? There's more nutrients, it means more food, more algae growing. Why though?
No, more
You're
algae
shaking your head.
means less sunlight.
Ah, yes, couple of reasons here. You see where all the life is in a yes, it's in that sunlit area at the top. There's so much algae, it's so thick with algae in that top layer, the sunlight doesn't even penetrate down here. So if there's no sunlight down here, what process will not be occurring down here? Photosynthesis. Here, oh look, photosynthesis is happening. Whereas down here, none. It's too dark. But something else, some other process is happening down here. What process is going on? Yes, decomposition, because algae is great. It can bloom. It can rapidly respond to those nutrients and grow like crazy, but they don't live very long. Algae dies like crazy as well as growing like crazy. And when it dies, it sinks, and decomposition happens. So you get, here's your oligotrophic lake, crystal clear, oxygen high, all the way to the bottom, because you got photosynthesis all the way to the bottom. Whereas in a eutrophic lake, you've got loads of biodiversity up in the top layer here, nothing down here. It's a hypoxic zone, it's dead, there's very little oxygen, it's dark. Look at the oxygen here, it's high, 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 and then suddenly it goes off a cliff. Because the dominant process in the eutrophic lake is decomposition down there. Yes?
So would it be low biodiversity?
It is low biodiversity. Well, it's not as low as oligotrophic, but it is low. It's lower than the mesotrophic lake. This is where you get the most life, is in this type of lake. But think about where you find these. These you find at the headwaters in a watershed. These are slightly further down where we are down here in the floodplain, Mississippi River, or whatever river, what other river comes through here? Is it?
Yeah.
Oh yeah. So you're in that floodplain, right? I'm sure you had flooding down here. In fact, a couple of years ago, you had a really bad flood. So you get tons of nutrients, tons of algae. All of our lakes around here are eutrophic. Doesn't mean it's bad. That's natural. Humans can make it worse. We call that cultural eutrophication. Okay. We're going to finish with two things, because we're not going to finish up, we're not going to talk about the ocean. We'll talk about two different ways to describe the zones of a lake or a pond. You've got, if you describe it by temperature, you might have noticed this. Have you ever gone swimming in any of these lakes? It can be warm at the surface, but you dive down a little and suddenly it's like, whoa, what happened, right? Really cold down there. It's because the temperature change is sudden. You've got this region called a thermocline, where you get a sudden temperature drop, and it's because of when the water isn't moving, it doesn't mix very well, right? You just get warm water sitting on the top, and then everything's cold underneath that. It doesn't mix a whole lot. If it was moving, it would be, same temperature top to bottom, but it's not. So you get the epilinean is where it's warm, the hypolinean is where it's cold, and then the thermocline is where you get the rapid change. And you can see it here. Here's the temperature. It just drops off a cliff very quickly. But there's another way to describe the zones of a lake, and here it is. This is the one you'll see more often. I hardly have ever seen a question about the temperature zonation. You just need to know it gets colder when you go to the bottom. Have seen many questions about the sunlight areas of a lake and the life that's found in these regions. Where would you expect to find most of the biodiversity in a lake? Which zone? 1, 2, 3, or 4?
1.
It is 1. Now why do you think it's 1?
More plant life, more things eating the plant.
Why is there more plant life? You're right. Well, yeah, why? Why is there more?
More sunlight.
Nutrients and sunlight all the way to the bottom. Why is there more nutrients on this zone than anywhere else? Think about it. How do the nutrients get into a lake? Yeah, right, runoff, right? It washes in. So this is the first zone to receive the nutrients into a lake. So lots of nutrients. You've got, it's shallow, so plants can root on the bottom and put their leaves up through. So you've got those two combinations create high biodiversity. And think about this. You've got two different life zones meeting, terrestrial and aquatic, in the same place.
Yeah.
Nicholas Wagstaff, Shamaria Views, Reagan Sunday.
Here's the word we use for moving.
Ella Atkins,
Lotic.
Karen Collins, Jacob Hoopy, Caitlin Boutwell, and
Last
Rebecca.
question. So what do you think? We'll finish with this. I don't like this question. It didn't come from an AP exam. Because I think it depends on a couple of things. What would you choose between? What would your two choices be? B and C? Yeah, I agree.
Yeah, B and C.
Now, they think the answer is B. I think it depends on the size of the lake. If you're talking about total photosynthesis, if it's a 100-acre lake, you've got a littoral zone around the edge, but most of the lake, you've got this sunlit area full of algae, you could get a lot of photosynthesis there. If the question was biodiversity, then for sure the littoral zone. But it depends on the size of the lake. All right, guys. You guys have been awesome. Good luck in the spring. I might see you again. Hopefully. You're welcome. Good luck. One more session.